So we know light is a wave, and it's an electromagnetic wave or electromagnetic radiation. And we can do some work calculating what happens when light interacts with materials using the wave properties. But very often we don't have to do all of that. We can just think of it as something that travels in a straight line. And so we're going to look at a section of optics called geometric optics, where we really are relying on this idea of light traveling in a straight line, and in fact, our eyes treating all light as coming in a straight line. And that's how mirrors and lenses work, is that our eyes interpret light rays as coming from straight lines, from straight paths, but it allows us to see different things. So we're going to start with reflections. And we can think of this as just a billiard ball model of light. In other words, light hits a surface, it's traveling in a straight line, it's not absorbed. I mean, sometimes it is, obviously, but it reflects back. And any light that's reflected is light that we have the opportunity to see. And so we can put our eye over here. This is the gigantic eyelashes there. That's light that our eye collects, okay? And that allows us to see things, right? Things that we see, it's because light has bounced off of that surface and comes into our eyes. Our eyes don't put out light beams, right? They're just detectors of light. Light comes into our eyes. So we're good visible light observers. We're not very good at infrared light observing, right? But night vision goggles do that. They can convert infrared light into a false color that then gets put in the visible for us to see, okay? So when I think about Superman having X-ray vision, there are not a lot of X-rays generated out in the world, which is generally good for us. So I guess Superman has some kind of a generator in his eyes that sends the X-rays out, and then he gets the reflections back. That's the way the X-ray machine works, is it sends it out and then looks for the reflections back. Okay. But back to normal humans, looking at, not superheroes, looking at light that's bouncing off of surfaces. And so our very common experience of this is with mirrors. And so if we're looking at something in a mirror, so we set up a mirror here. So this is my mirror. And we have, say, something down here, a flower, for example. There we go. And we have light that comes from some section of the flower, like here. And then what we're interested in when we have reflections, we say we have the same angle in as that comes out, the reflected. So incident and reflected light. And so if I set this up, we do it in relation to the normal of the surface in case the surface is curved. So we say the angle in equals then this angle out, and this can again come to our gigantic eyeball to see that part of the flower. And so another section of this might give us something that, well, actually, if we're going to go to the eye, let's see, I'm going to come and let's do it like this. Oh, I'm not very angle in. I want it to come from the same spot. These are just sitting right on top of each other. There we go. Ooh, that's bad. Okay, so the point is that from your eye's point of view or your brain's point of view, all of this light, all of this is now big beam of light coming from this flower, hits the mirror and then hits the eyeball. And so from your eye's point of view, you think it comes from a straight line. You translate it. And so from your perspective, this flower is behind the mirror, the same distance away and the same size. So this is the image that you see. This is the object. But if you're looking like that, in fact, if we put a block right here, right? You could still see this. That's what the mirror does. It allows you to kind of see around a corner. If, for example, we put a blockade up here, you could still see. That mirror allows you to see this image, this flower behind the mirror. So from your perspective, this flower doesn't live at the mirror. It lives behind the mirror, the same distance behind the mirror that it was in front of it. So this distance, D, is equal to this distance right here, okay? So with a flat mirror, this is what we see. So if we look at ourselves in a mirror, so here's a mirror. Let's see, here we go. Yeah, I know, arms are not halfway down the body. But anyway, if, for example, we want to see our face, then like our nose here, then we would look for a light ray that's coming like this, going to our eyes, right? Angle in equals angle out, sort of right in the middle part here. If we want to see our feet, then we're looking at light that comes in and kind of goes up to hit our eyes like that. And if we want to see our knee, if this is our knee on this crazy stick person, then we're looking at light that comes up like that. Ooh, that's not at a very good angle for this. Okay, that goes in and then comes back out like that. And so again, you see this ray, if you follow it back, this becomes sort of your picture of your feet, right? And then this ray, if we follow it back from your eye, so this one, that's your nose there, and you can see basically your whole body, right? And that's how you see yourself. Notice you're only using a section of this mirror, right? You really only need from about here to see your whole body. So if you are like I am, and I'm 5 feet tall, then the size mirror that I need is really just 2.5 feet tall. Okay, it's half of my height, because that lets me see all of my body. I can see from my feet really to the top of my head, if it's placed just right. I mean, it has to be placed just right so that I can see my feet. Now, if we put someone taller, because most people are taller than I am, behind me to try to use the same, or beside me to use this same mirror, then we can end up, okay, so now we're going to have a really tall person, a gigantic person. Notice that, first of all, this person needs the mirror to be taller up here. Yeah, on this scale, this is now a 7 or 8 foot tall person. And the bottom of the mirror needs to be about here, right, to go like that, to see, for this person, this very tall person, for them to see their whole body. And so this person, if they're, we'll say, 7 foot tall, then they need a mirror that is 3.5 feet tall, but they need it placed in a different place. And then if we have some little kid who's only, I don't know, 3 or 4 feet tall, then we have the little kid down here, then of course they're going to need a mirror that's half of their height. So the reason that full-length mirrors are as big as they are, even though you personally don't use all of the full-length mirror, I certainly don't, the reason they're as tall as they are is because people come in different sizes. So when you want to see actually your feet, you really don't have to have a mirror that goes all the way down to the floor. The reason, for example, in bathroom mirrors, that even if they come down to half of your height or something like that, like they come down to here, most of the time we don't see our feet because the light that would be coming from our feet is actually blocked by the sink. If the sink weren't there, we could actually see our feet. And that's why we sometimes have mirrors and then we back up to try to see more of ourselves. It's because the light is reflecting off of whatever it is, but then getting caught by whatever is down below, the dresser or the sink down below. So for a good full-length mirror, you just need it to be half your height, but people come in lots of different sizes, so we need the full length. And all of this is just coming from right? Your eye getting in some ways tricked that you don't know that the light has changed directions. The way we interpret it is the light is coming in a straight line, and that's what allows us to use mirrors, which is really convenient, and to see things, right? That's how we know where things are, is by these reflections.